Hi everyone, welcome to lecture 13 of ATalk 1050. Please refer to lecture 12 for the latest announcements and updates of this class. And now we'll just jump right in and pick up where we left lecture 12. So where were we again? This is the last lecture that will deal with chapter 8 about wind. So chapter 8 more specifically deals with the geostrophic balance, which is the balance between pressure gradient force and Coriolis force and the resulting geostrophic wind. We discussed geopotential height as well. And then we discussed how jet streams are a prime example of this geostrophic balance and geostrophic wind. Then the last lecture, we discussed that the atmosphere is really rarely in geostrophic balance. So in upper levels, we have a balance that is so-called the gradient wind balance. Can you remember which three forces are behind the gradient wind balance? Yeah, so it's a balance of forces between the pressure gradient force, Coriolis force, but those two are no longer in balance. There is a third force that is the centripetal force, which is always directed inward, so towards the center of the low pressure and high pressure system, doesn't matter, always directed inward, which leads to the curvature of the wind vectors around the low pressure and around the high pressure systems on the northern hemisphere as well as the southern hemisphere. So we talked about the direction of flow in each of those systems, so counterclockwise or clockwise, and why that is. So hopefully you remember all of those, as well as the difference between upper level weather maps and surface weather maps, which I will briefly recap in the next slide. But really today I want to talk about the last effect or impact of the lack of geostrophic balance, especially close to the surface. What is going on there and what is the result? And then the second part of this lecture will start with the new chapter, chapter 9, which is really putting our knowledge about wind into practice and looking at different wind systems on Earth. So weather maps, we have a really clear distinction between weather maps in the upper levels and weather maps at the surface. So in upper levels, we show geopotential height contours. We can ignore friction, and the winds tend to be close to, but not equal to, the geostrophic winds, where the pressure gradient force and Coriolis force balance each other. There is usually the so-called gradient wind balance, where we have this third force, the centripetal force. And the flow is always parallel to geopotential height contours. And you can see the example here of a northern hemisphere low pressure system upper levels, and a northern hemisphere high pressure system at upper levels. Okay, so these contours are geopotential height contours. The flow of the winds is counterclockwise here, low pressure system clockwise here in the high pressure system. At the surface, it's different. Surface weather maps show isobars instead of geopotential height contours, so lines of constant pressure, air pressure. Friction is important, which means that the winds tend to flow across isobars because of friction. And they are curved such that they move inward in a low pressure system and outward in a high pressure system. Okay, so this is really important to understand what happens between a low pressure system and a high pressure system. I'll come back to this in a bit. Okay, so this is on the top, typical example of an upper level weather map, and at the bottom you can see the surface weather map. And just to remember or highlight this again, so we see the arrows of the winds curving inward for low pressure system at the surface, and outward around the high pressure system at the surface. Okay, so this is interesting. We need to look into this a little bit more. Okay, what's really the driving force behind all of this? Well, if we look into this low pressure system, for example, we see that there is net inflow of air because the wind arrows are directed towards the center of the low pressure system. Okay, do you see that? And this is what we refer to as convergence, okay? There is really air piling up inside the low pressure system at the surface. And this is really what we refer to as convergence. And why the wind does this is because it wants to get rid of this low pressure. It wants to fill up the low pressure with more air. Okay, so it's basically the wind trying to reduce the pressure gradient that exists between the center of the low pressure system and the outside of the low pressure system. And this is really important. This convergence at the surface is a really important aspect of the formation and the existence and the development of low pressure system. And it's all due because of convergence. And convergence is an effect of friction at the surface. And because the air is converging in the low pressure system, that leads to rising air as a result. Okay, so because the air is piling up at the surface, it has no other way of leaving the surface in the vertical direction. Okay, now the opposite is true for a surface high pressure system where we have the wind vectors directed outwards, right? So that high pressure system at the surface is experiencing divergence. So air wanting to leave the center of high pressure system, because it wants to get rid of the pressure gradients between the high pressure center and the lower pressure outside of the system, okay? So as a result of air wanting to leave the high pressure system, there's sinking air. There's coming air from above towards the surface. So vertical motion in terms of rising air, as we know, this is convection, right? So this is the weather that belongs to unstable conditions. Thunderstorm development, for example, cumulonimbus clouds are associated with rising air. Okay, and that rising air again is also associated with convergence in a horizontal direction. So convergence is an atmospheric condition that exists when the winds cause a horizontal net inflow of air into a specific region, for example, a low pressure system at the surface. Okay, so in other words, convergence adds mass to the column of air, and that convergence, if nothing would happen, would lead to a surface pressure increase. Okay, so because of this adding of mass, the surface pressure would increase, but it does not because the air rises. So that's kind of the association or the link between horizontal and vertical movements. So convergence can be caused by two different processes. The wind direction that changes, so winds are directed towards each other. That's what happens at the surface low pressure system. Or changes in wind speed, and that's what happens in higher levels. Okay, so we've seen that this convergence, this winds coming towards another, happens at the surface low pressure system. And at the same time, changes in wind speed sometimes happen in the upper air around a high pressure system. You don't need to know why this is, but because faster winds approach slower winds, there are changes in wind speeds. There is air piling up above, so in the upper levels around the high pressure system. Okay, so we have convergence at the surface in a low pressure system and convergence at higher levels above a high pressure system. And divergence is the opposite, right? Where the winds are directed away from each other, or where slower winds approach faster winds. Each of those leading to a mass removal from a column of air, okay? And wind direction changes as in the form of away from one another happen at the surface of a high pressure system. And you need to believe me that sometimes changes in wind speed when slower winds approach faster winds, that sometimes happens in the upper air above a surface low pressure system. Now, so to recap, we have convergence at the surface in a low pressure system and divergence in the upper air, right? While we have divergence at the surface of a high pressure system and convergence in the upper air. Now, why is this? And why is this so important? Well, It's because this convergence at the surface of a low pressure system leads to rising air, and that air, when it reaches the top of the atmosphere, diverges. Okay, so we have convergence at the surface associated with divergence aloft. And that's important because we'll need to get rid of this rising air. It needs to go away at the top of the atmospheric column. Otherwise, the mass would pile up in this column and the low pressure system would actually dissolve because the pressure would rise as a result of this mass pile up in the column. Okay, so that's why it's super important for low pressures to maintain themselves, that this divergence happens aloft in the upper levels of the atmosphere. Same is true for a high pressure system, where we need convergence in the upper levels in order for the sinking air to happen, in order for this divergence to continue to happen. Okay, so we need to get rid of this this mass here, and we need to add mass here in order for the low pressure to remain low and the high pressure to remain high. Okay, so hopefully this makes sense. What you need to remember is how this convergence at the surface is associated with divergence aloft and why that is. And divergence at the surface is associated with convergence in the upper levels and why this is so important. Okay, again, it's important to sustain these low pressure and high pressure systems at the surface. Okay, so this was the end of chapter 8, and let's now move on to applying our knowledge in the last 3.5 lectures about wind and apply that to different systems on Earth. So chapter 9 evolves around global wind systems. How are winds generated, and what kind of circulations do we know exist on Earth? Now, it's important to separate the different categories, and there are 3 major categories of atmospheric circulation. Firstly, there's macro scale, then there's mesoscale, and then there's microscale. Now, what do these mean? They mean, or they are associated with different scales of time as well as space in which they exist. Okay, so what does this mean in particular? We have macro scale winds that are interplanetary, and planetary means that there are very long time scales and very large spatial scales. Okay, weeks are longer and larger than 1,000 up to 40,000 kilometers. So for example, we talked about the atmospheric westerlies, talked about the jet streams. Another example is trade winds, which are happening closer to the equator, which we won't talk about today, but these are also very, very large systems. And then the second type of macro scale winds are synoptic scale winds. And these are associated with mid-latitude cyclones, anticyclones, as well as hurricanes, which are tropical weather systems. They exist for days to weeks, and they have a distance scale from 100 up to 5,000 kilometers, okay? Then within those larger systems, there exists a variety of smaller systems, okay? We have mesoscale winds, which we'll talk about a little bit today, which have time scales from minutes to hours and distance scales from 1 to 100 kilometers. For example, thunderstorms, tornadoes, as well as land sea breeze, which we will refer to later in this lecture. And then finally, we have the smallest scale winds, which also are the shortest. They exist only up to a few minutes. They have a distance scale less than 1 kilometer. And examples of those are turbulence, dust devils, and gusts. We'll talk about those as well. So it's important to acknowledge that these scales of circulation exist in one another. Okay, so if you look at this plot, this shows time on the horizontal axis and space on the vertical axis. Okay, from time being very short to very long, from left to right, and space from being very small to very large, from bottom to top. Okay, and these different patterns or scales of circulation exist within this parameter space, if you will. Okay, the smallest exist on the lower left, and the largest exist on the upper right. So the smallest are eddies, turbulence, for example, that are very small and also very short-lived, while the longer and larger systems move towards top and towards the right of this graph with the longest and largest planetary scale systems all the way to the upper right. Okay, but we need to acknowledge and know that these smaller systems exist in larger systems. So, for example, there's turbulence existing in hurricanes. Okay, there are fronts that exist in the large-scale waves in the westerlies, in the jet streams, for example. So smaller scale systems are part of a larger scale systems, okay? And all these larger scale systems have smaller scale systems embedded within them. So let's move on from very small and very short-lived events to all the way planetary scale, okay? First of all, we have the micro scale systems, and an important example is turbulence. Turbulence exists because the wind encounters a solid object, and that object will create a whirl of air or an eddy that forms on the downwind side of the object, okay? And that creates wind shear. That's nothing else than a rate of change or wind speed or wind direction over a given distance. So these clouds that you can see here are the famous von Karman clouds, and they exist because the winds are slow at the bottom, and they're higher aloft. Okay, so that creates this wave in the cloud that you can see in this picture. So turbulence exists everywhere in the atmosphere. It's usually invisible, but sometimes you can see it in clouds or in satellite images. So it exists everywhere all the time. There are also eddies that are a little bit larger, and an important one for us living here in the eastern side of the Rocky Mountains are rotors. Rotors are turbulent eddies that form downwind of a mountain chain. So remember, we have the Rocky Mountains and we have typically westerly flow. And as the westerly flow approaches the mountains, it needs to lift, okay? And then descend again on the downwind side. And that creates waves in the atmospheric flow because of the mountain range. And beneath these waves, we can get eddies where the flow gets extremely turbulent. And I don't know if any of you have ever experienced turbulence when descending into Denver Airport, Denver International Airport. Well, that's due to these rotors that exist within the downwind pattern of the westerly flow, because the Rocky Mountains are really forming this barrier, okay? And these rotors sometimes can be extremely powerful. So powerful that we get a lot of damage in Boulder, for example. So this is an example of winter 1982, when there was a lot of damage associated to a rotor that was associated to downslope winds. We'll talk about downslope winds in a little bit. And these rotors can be so powerful that they take down power lines. They make windows of cars pop, and they can also create damage of a variety of kinds. So this is an example of February last year. And these are pictures that I took when I went to university. Trees being destroyed because of very, very strong gusty winds up to 60 miles per hour the night before. So these rotors can be extremely powerful. Another example is our dust devils, and dust devils are small scale winds that can that look really beautifully. I will show a video in a few seconds. And these are spinning columns of air that form on clear hot days over typically a dry surface. And we can see these because they typically lift sand into the atmosphere. And I'll show you an example right now. Okay, let's move on to the mesoscale, which is this in-between scale between a micro scale, small scale, and a macro scale, the very large scale. Mesoscale is kind of like 1 to 50, 100 kilometer spatial scale. And one really clear example are these thermal circulations. We've talked about thermal circulations previously, and these thermal circulations are really a great example of mesoscale circulations. A great example of mesoscale thermal circulations are the land sea breeze, or the sea breeze during the day and the land breeze during the night. Okay, so I invite you to draw a beach and to draw an ocean from left to right, and think about the daytime situation. Okay, so let's derive the thermal circulation that occurs every day on the beach, where the beach gets warm and the ocean is still cold. Okay, and apply the knowledge that you know of a warm column and a cold column, and try to follow these guidelines as I put them here. Okay, good luck. Okay, so recognize this. This is this thermal circulation, right? Because there is a airflow in the upper layers associated to the warm column having high pressure, cold column having low pressure. So there is a pressure gradient force from high pressure to low pressure, so from right to left, and that leads to mass pileup here, which leads to downward motion, which leads to high pressure at the surface and low pressure here. So we have this thermally direct or thermal circulation complete. Okay, so a combination of horizontal flow, vertical flow, and the sea breeze is a really great example of that, as shown here. So we have a pressure difference between land and sea in the higher atmosphere because of pressure differences. So pressure differences, or sorry, because of temperature differences. Temperature differences create pressure gradients. Pressure gradients create wind. Okay, and as this upper air circulation develops, we'll have a vertical component, so descending motion over the ocean, and a rising motion over land. And the sea breeze is this surface component of this circulation. Okay, so sea breeze brings this cold air from the ocean towards the land. And that's why sometimes when you're on the beach, especially in early summer, you can have this very strong influence of the sea breeze. The temperatures over the land can drop by 5 to 10 degrees C in a matter of minutes. It can affect areas up to 100 kilometers inland, and these winds can be pretty gusty as well, and typically occur in the mid-afternoon, I should say. Okay. So my question to you is, what do you think happens during the night? Do you think the situation remains the same, or do you think it changes? Yeah, so at night we see, as you would hopefully have thought yourself, the opposite would happen, where the water is still relatively warm and the land cools off more rapidly. Okay, so in this case we have a surface wind that looks like this from the land towards the ocean. So this is what we call a land breeze. Okay, so we have a sea breeze during the day and a land breeze during the night. Okay, all right, other mesoscale winds there are many examples of mesoscale winds, but this is one that is very important to my research. And these are called katabatic winds. There are strong downslope winds that happen especially over ice sheets. Okay, and these strong downslope winds exist because there is higher pressure in the interior of ice sheets and lower pressure around the edges, and that creates a pressure gradient force, which is actually helped by gravity because these winds are downslope. They are descending. And these katabatic winds can be extremely powerful. Okay, so the ideal conditions is an elevated plateau surrounded by mountains where there is a valley that slopes rapidly downhill. And it really helps if the surface is snow covered, because then it's really cold and you have a strong temperature inversion. So Antarctica is a really important place where katabatic winds are very strong. And has been known for a very long time, actually since the beginning of the 20th century, when the first adventurers tried to approach Antarctica. So this is an example from the Australians who tried to reach Antarctica from Hobart, from Tasmania, and got there in 1912. So more than 100 years ago, they reached the coast of Antarctica here. And they were a little unlucky because, as we know now, this place around Antarctica is a place where the katabatic winds are actually strongest. Okay, so they built a hut there, and as you can see here, the winds are pretty strong basically all the time. Okay, this hut, by the way, still exists as of today, but is completely buried by snow because it's so windy there. And this is what kind of observations looked like 100 years ago. Okay, I want to show you what these look like. These are obviously written, so they're not digital, but I want to show how strong the winds are where their hut was on Mawson. And you can see a 14-day period here where the winds did not go down lower than 50 kilometers per hour, up to 150 kilometers per hour. So almost 100 miles per hour winds, basically all the time. Okay, so this is an extremely windy place, maybe the windiest place on Earth, which they refer to in their book, Home of the Blizzard. Actually, another expedition was sent out around the same time. They also measured wind speed, and you can see how much lower the wind speed was in that other location, just a few 100 kilometers away from this Mawson location. But we also have strong winds closer by, actually in Boulder itself. So I gave you an example of the rotor already. And this rotor is a microscale example embedded within a mesoscale circulation called the Chinook winds. Okay, and this is showing an example of a arrival of a Chinook wind, where at around 10 a.m. in the morning, the temperature increases very suddenly. The dew point decreases very suddenly, so that's associated to a decrease in relative humidity. And this is all associated to and explained by a very strong increase in wind speed. Okay. Now, why is this? Well, we already know this, right? Because it's associated to the existence of the Rocky Mountain mountain range that interacts with the prevailing flow from the west. Okay. And the atmospheric flow needs to lift on the western side, the windward side of the Rocky Mountains, which leads to precipitation, which leads to cooling, obviously, as well. And typically, when the air reaches the top of the mountain, all the precipitation is gone, and the parcel is unsaturated again, at which point, when it starts descending, it follows the dry adiabat. So it typically follows the wet or moist adiabat on this side and the dry adiabat on the downwind side, which means that the air is extremely dry and also warms up very rapidly as it descends from the mountain range. Okay, and these are so-called Chinook winds that are also called föhn winds in the Alps, and have different names all around the world because they exist in many places. And they can lead and explain a very strong temperature increase on the east side of mountain ranges, such as in Boulder, for as much as 20 degrees C in a matter of minutes. So these are really impressive events that occur regularly here in the winter and in many other places. An even more, I think, extreme example is in a Haboob, which is a large dust storm that is formed in the desert and is associated to downdrafts. We'll talk about downdrafts later in the semester, associated to thunderstorms. And this cloud of dust can extend over 100 kilometers and up to several kilometers in height. And I'll show you an example of an arrival of an Haboob in Phoenix, Arizona. Okay, so let's move on one category higher and look at macro scale circulations. Macro scale circulations, remember, are large scale circulations that exist days to weeks and are 1,000 kilometers or larger. So one really important macro scale circulation is a monsoon. Let's look at a video first. Yeah, so the monsoon is a wind system that exhibits a very clear, pronounced seasonal reversal in direction. And it's associated, just like the sea breeze, by a difference in temperature between land and ocean, okay? In the winter, which is seen here on the left, you have a high pressure system of the cold and dry Siberian mainland and a low pressure system above the ocean. And that leads to a net flow from the land towards the ocean, okay, because of the pressure gradient force. In summer, this circulation reverses, where the low pressure system is above the land, leading to flow from the ocean towards the land, and that's creating or bringing very warm and moist air from the ocean towards the continent. So in winter, this area is typically very dry, and in summer, this is very wet, okay? So this is what you can clearly see here in an example of a location in India, where there's almost no winter precipitation, or actually no, in January and December, and then so much precipitation, a lot of precipitation in summer. So these are extremely high precipitation, monthly precipitation rates measured here in this area due to the monsoon, okay? So this is called the Indian monsoon. We also have a similar but a smaller version over the North American continent, where again Arizona experiences a similar pattern with very dry winters and then a short period of time in summer, in July and August, where it actually rains much more. Okay, so in late summer, fall season, we get this moist air transport from the ocean towards the land, which leads to summer precipitation. And then last but not least, an example of a macro circulation that involves the ocean, the interaction between the ocean and the atmosphere as well, and that is known as El Nino Southern Oscillation, or El Nino itself. And El Nino is a manifestation of cold water upwelling along the coast of South America and around the equator. And I'll show you a video to illustrate what the monsoon is. Oh, sorry, excuse me. What El Nino is, which explains a little bit more detail about the physical mechanisms. Yeah, okay. So as we just mentioned, also El Nino is kind of an example of thermal circulation, where we have high pressure systems where it's cold at the surface and low pressure systems where it's warm at the surface, which leads to a thermal circulation that looks like this in El Nino situations. And in La Nina situations, which is kind of the reversal, we have an opposite situation where the high pressure system is actually above Indonesia in this case, and the low pressure system is moved east. So in this case, this La Nina situation, we get a lot of dry conditions above the Asian and Indonesian and Australian continents, and much more wet conditions on the Pacific Ocean itself. While El Nino is typically associated with very, very wet conditions in these areas of Asia, Indonesia, and Australia. So this is El Nino situation typically leads to flooding problems in these areas, while this La Nina leads to dry problems with drought and wildfires and similar phenomena. For the North American continent, it's a little bit less clear. but typically El Nino conditions are associated to cooler and wetter than usual conditions in the south of the continent, because the jet stream is displaced south, and warmer than usual in the Pacific Northwest, Alaska, and coastal Western Canada, while the reverse is true for La Nina. And why is this important? Well, because I want to mention that this winter is very much shaping up to be a La Nina winter, with the blue bars here showing the probability for La Nina to continue into the winter. So this is show the months, August, September, October, November, and so forth. And you can see that the probability for La Nina remains extremely high, basically until the end of the upcoming winter. So this will be associated to conditions that looks more similar like this, with the high pressure in the Central Pacific, and then colder than usual and wetter than usual conditions along the western coast of Canada, as well as the Pacific Northwest, and warmer and drier than usual in the southern part of the US. And that's bad news for places like Arizona, southern Colorado as well, which are already very dry and will probably experience a very warm and dry winter. So this shows a seasonal prediction of the geopotential height contours and how they differ from the normal situation. So this is for January, just as an example. And just as what I showed here, this looks very similar. So because of La Nina, we will see very high geopotential heights in the Central Pacific, and then low geopotential heights along the western coast of Canada, as well as the US, and then also high geopotential heights in the southern part of the US. So this looks very similar than the kind of sketch picture shown here. So La Nina is going to rule our winter in the next few months. Okay, so that's it for lecture 13. I hope you enjoyed this lecture. Let me know if you have any questions. Thank you.